All right, so welcome back. So today we're going to talk about local extreme values, local minimums and local maximums of graphs. So we're going to use calculus to help us figure that out. So a reminder, what is a local maximum and what is a local minimum? So a local maximum is the output value. So we were going to report the y values when we say our maximums and minimums. The output value where a function changes from increasing to decreasing. So if we're thinking about a function that goes from increasing to decreasing, then that point at the top is sort of the highest locally, the highest one in its neighborhood, and thus would be the local maximum. Again, we want to report the y value because we're thinking about like how high up it is. Okay, and then the minimum, very similar. It's the output value where a function changes from decreasing to increasing. So that would be in a case if this continued on, if it decreased and then increased, then that y value is the lowest in sort of that neighborhood, so it is a local minimum. Sometimes these are also called relative maximums and minimums. So if you see that, it means the same thing here. All right, so let's do an example of this. So I gave us a pretty fancy function here. F of x equals x squared times x, 6 minus x to the negative third power. So you could take that right now and move along with it, but I think I'm going to actually rewrite it as a quotient just because I think it's going to make my life a little bit easier here. But you could actually move forward with how it is, and it'll work out. Okay, so first thing first, we are going to find the derivative. Why are we finding the derivative? Well, if you remember, the derivative tells us the slope of the tangent lines, and so that'll give us a really good idea of where our graph is increasing and decreasing. And then from there, we can go ahead and actually come up with the values. So that's why we're finding f prime. So here we go, derivative of the first thing times the second thing subtracted by the derivative of the second thing. So the denominator is a quotient, or a composite function. So I'm going to use the chain rule. So something cubed, its derivative is 3 something squared, and then the derivative of the inside is just going to be -1. And then that's times the top thing. All over 6 minus x cubed squared. All right. Let's make this look a little bit prettier here. So we got 2x times 6 minus x cubed. And then here we've got a negative times a negative, so it'll be plus 3x squared times 6 minus x squared, all over 6 minus x to the 6th. Okay. So what I notice is that in my numerator I have two terms here. I've got this big chunk here and that big chunk there. And they have some common factors that I can pull out. So let me further sort of show what I'm seeing. So I see this and this. Those are the two terms. Right now it is written as a sum. So if your sort of inclination was to really go like, oh, I'll just divide those things. Remember, you need a product in the top. It's a sum right now. We've got two things being added together, not two things being multiplied. So let's get this rewritten. Let's factor out some stuff. So they both have an x in common. So I'm going to pull out an x. They also both have a 6 minus x squared in common. That one has 3 of them, that has 2 of them. And so what gets left behind? So let's take a look at this first term. I factored out the x, and I factored out 2 of these. So I'm left behind 2 times 6 minus x. And then here, I factored out one of these x's, and I factored out both of these 6 minus x's. So I'm left with just 3x. Now the reason I'm doing that is twofold. In a moment, I'm going to want to solve for when this is equal to 0, and having it written as a product, which it is now, is more easy to deal with because things multiplied equals 0. We know how to deal with that. The other thing is I now have a common factor in the numerator and denominator. See, this is a product. That's 3 things being multiplied. So now I can divide those things. So that's going to leave me with x times, I'm going to go ahead and distribute and combine. So it's going to be x minus 12 in the numerator. And then down below, 2 of those divided with those 2 up top. So all I have is 6 minus x to the 4th now in the denominator. All right. Let me double check my stuff here. So that's x. And then here, negative 2x plus 3x is 1x. And then, plus 12. Plus 12. All right. I think I got it. Okay. So now, what do I do with this information? Well, now we try to find something called the critical numbers. The critical numbers. The critical numbers are when you're interested in when f prime of x is equal to 0 and when f prime is undefined. That's where critical numbers happen, because that's where the possibility of changing direction might happen. If it's going to go from increasing to decreasing, it might level out like these ones here. But it's also possible that it might change when, like, these are pointy or cusps or corners or whatever we called them in class, like absolute value functions. So like an example would be, it could be like this. And in which case, those places are not differentiable. The derivative is not defined there. And so that's a good place to look as well. So all of our candidates for maxes and mins are coming from just these 2 places. If f prime is any other number, then it means that it's increasing or decreasing at that point and not actually a max or min. So let's go ahead and find these things. So when is f prime equal to 0? So x times x plus 12 over 6 minus x to the 4th equals 0. Well, if we multiply both sides by the denominator, we just get x times x plus 12 equals 0. Also, a fraction can only be 0 when the numerator is 0. And then now I have 2 things that equal 0, so either x equals 0 or x plus 12 is equal to 0. That one's already solved. This one gets us negative 12. All right, so the first 2 places we could be looking are at 0 and at negative 12. All right, now let's look at when f prime is undefined. Well, a fraction is undefined when the denominator is 0. So I will set the denominator equal to 0. And you can quickly see that x has to be 6 in order for that to be the case. So there you have it. I have 3 candidates for where the maximums or minimums might be happening or occurring for this function. So now it's time to go take a look and see if they are maximums, minimums, or maybe none of those things. It's possible that the function sort of has leveled out but didn't actually change direction. It's also possible that I'm looking at maybe a hole in the graph or a jump discontinuity or an asymptote, in which case that doesn't really fit the definitions either. Okay, so how do I do this? Well, there's a lot of ways you can go about figuring out whether these are maxes or mins or nothing. I use sign analysis, so that's what we're going to do now. So down below here, I write down first all of the factors from my f prime in the left column. So we got x plus 12, and then we've got 6 minus x to the 4th. And all of those build up f prime. And draw a little table. And now I'm going to break up the function, or sorry, the real numbers based off of these three values. So here's what I mean. So starting at negative infinity, we get to negative 12 first, moving to the right. And then negative 12, picking up on the other side, 0 is the next place we stop. And then 0 to 6. And then lastly, 6 and beyond. All right. So there's my sign analysis charts that I'm going to make. I make this because I like to break it into small pieces. I tend to make really small errors all the time. So here we go. We're just going to analyze the sign of each of these pieces, and we know that we will multiply, divide by, and when we know that things are positive or negative, we know the rules for multiplying and dividing really quickly. It's better than adding and subtracting. So that's a really important thing, is like, you don't want to put in individual terms, because adding and subtracting positives and negatives, those rules aren't as clear cut as multiplying and dividing. So here we go. So in this interval, you can think about a specific number. If you plug it in, what do you get? Well, here we get negative. It stays negative, x. Then it switches over to positive, and then positive. All right. Here, again, you can think about a value. If you plug in like negative 16, you're going to get a negative. But here, if you plug in like negative 8, you're going to get a positive from x plus 12. This will be positive. That will be positive. Last one, you don't even have to think about here because it's to the fourth power. And so anything to the fourth power will always be a positive value, or 0, but we've removed when it's 0. The 6 is where it's 0. So positive, 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 positive. Okay, so now it tells me the overall sign for f prime. So here we got a negative times a negative divided by a positive. That's positive. Negative times positive. That'll be negative. All positives are positive. All positives are positive. Cool. And then the thing is that you could actually create a different column or a different row down here. Sometimes I do it, sometimes I don't, where I write down, what does this mean for f? So that tells you what f prime is. What does this mean for f? Well, if f prime is positive, f is increasing. If it's negative, it's decreasing. Increasing, increasing. And so now that makes it fairly clear about where we should be looking, because we still have these definitions up here. So I want to look for where the function changes from increasing to decreasing to find a local maximum. Well, where does that happen? Increasing to decreasing, right here, at the x value negative 12. So let me find what f is at negative 12. So this is a local max. So this is technically a correct answer. F equals negative 12. But often I like to actually go a bit further. And so I'll go like, oh, negative 12 squared over 6 minus negative 12 cubed. So that's 144 over 18 cubed. What is 18 cubed? I don't know. I don't have my calculator near me. So, but that would be the output value in this particular case. All right. And now we think about local minimum. Local minimum occurs when the changes from decreasing to increasing. So decreasing to increasing here at 0. So I'll plug in 0. And I'm going to get 0 squared over 6 minus 0 cubed, which of course is just 0. And the last critical point at 6, it changes from increasing to increasing. Actually, it didn't change at all. Also, you would note that if we tried to plug in 6, we would get an undefined value. So there's an asymptote here So even if it did go like increasing to decreasing, when you plug in 6, since it's undefined, it wouldn't be either one of these things. Okay, so there you have it. Finding local maxes and mins. Let's do a quick rewind on it. So you use your derivative rules to help you find the derivative, because that's going to tell you the slope. Simplify as much as possible, because you're about to set it equal to 0, so you want it to be ready to rock and roll when that happens. So you set it equal to 0 and solve, and you figure out when it's also undefined. Use those values to break up the sign analysis and create a chart like this, which then tells you when it is increasing and decreasing, and from there interpret your results. Okay, we're going to do some practice on this and then apply it to our project. So make sure that you take the survey and ask me questions so that way we can be ready to roll on the next day. Thanks.